Now moving on to the last paper for this session, I would like to invite Mr. Ammar Akbar, and the paper title is Design and Prototyping of High Energy Density Electrical Machines for Gearbox-Free Powertrain of EVs. Mr. Mohammad Ammar Akbar is the electrical engineer and manager research and development at Power System Research Lab at NUST, Pakistan Navy Engineering College. He holds a master's degree in electrical engineering from National University of Science and Technology with distinction. His research focuses on power system analysis, smart grid architecture, industrial automation, and power electronics, with a strong integration of machine learning, cybersecurity, and digitalization. He has led advanced research in EVs, charging system, battery management, renewable energy integration, and AI-based monitoring solution. His works include development of smart metering systems, servo drives, and intelligent safety mechanism for industrial applications. Over to you, Engineer Ammar.
Honorable chairs, fellow researchers, and industrial colleagues, Assalamu alaikum. It is a privilege to stand before the IEEE Symposium today to share our latest advancement in electrical mobility. The title of my presentation is Design and Prototype of High Energy Density Electrical Machine for Gearbox-Free Powertrain of Electrical Vehicle. Before I start the presentation, I must acknowledge that this research reached this stage under the visionary mentorship of Dr. Saeed Sajjad Haidarzadi. His guidance at the Power System Research Lab has been the driving force behind our pursuit of indigenous technological excellence. To provide a clear roadmap of today's discussion, I have organized my presentation into few key segments. Number one, the local market need. Number two, the core problem statement. Number three, motor design evaluation. Number four, fabrication process. And the last, performance validation. Moving forward, we must address the fundamental why behind our research. As we enter 2026, Pakistan automotive sector is at a crossroads. While we see a surge in EV interest, our industry still faces a critical bottleneck, which is import dependency. Currently, Pakistan relies heavily on imported technologies and completely knocked down kits. This means that even as we transition to electric mobility, our economy remains vulnerable to global supply chain fluctuations and high import duties. As you can see in the diagram, the powertrain is the heart of the vehicle, yet almost every component from the traction motor to the controller is currently sourced from abroad. The problem statement. Now that we have established the market need, let's look at the technical bottleneck that currently hinder EV development in our region. The traditional approach to EV powertrain relies on high-speed motor paired with a mechanical gearbox. While this works, it introduces several critical flaws. First, mechanical transmission are a primary source of power loss due to their friction and heat, which directly reduces the overall vehicle range. Furthermore, these gearboxes add weight, complexity, and significant mechanical requirements. When we look at the motors themselves, the industry standard often involves permanent magnet machines. While efficient, these motors are incredibly costly because they rely on rare earth magnet materials. These materials is not only inflate our production budget, but also tie us the volatile international market. As long as we rely on the imported high-cost machines, local scaling remains nearly impossible. Now let's discuss the design evaluation of this presentation. Once we identified the need of the gear-free box, high torque solution, our next step was determining the right motor topology. We began by analyzing the standard permanent magnet motors. On paper, they are the ideal candidate. They provide excellent high energy density and the efficiency requirement of modern electrical vehicle. However, as we moved deeper into the feasibility phase, we hit the same wall I mentioned earlier, the reliance on expensive rare earth magnetic materials. The cost of neodymium magnets fluctuate widely, and because Pakistan has no local source for these, using a PM-heavy design would create a severely dependency on imported materials. Having finalized our design topology, we move into the validation phase using advanced finite element analysis and simulation tools. The plot you see on the screen represents the rigorous testing of our high energy density machine. First, let's look at the torque, speed, and high efficiency maps by analyzing the current vectors. We were able to pinpoint the optimal operating regions for our motor. The goal was to ensure that even without a gearbox, the machine could deliver the necessary launch torque while maintaining high efficiency at cruising speed. A critical challenge in gearbox-free design is cogging torque, which can cause vibration and noise in an electrical vehicle. As shown in the cogging torque figure, we have successfully minimized these ripples through precise pole slot optimization. This ensures a smooth ride quality, which is often a trade-off in direct drive systems. To move from concept to a working prototype, we first establish a comprehensive mathematical framework. We began by driving the fundamental electromagnetic governing equations specific to our multi-stator architecture. However, a motor does not operate in a vacuum, obviously. To ensure our design could handle real-world conditions, we modeled dynamic road loads using MATLAB Simulink, as shown in the block diagrams on the right. We accounted for every physical force acting against the vehicle, such as aerodynamic drag, rolling resistance, gradient resistance, and acceleration force. By integrating these vehicle dynamics with our motor model, we calculate the precise speed torque requirements needed for a gearbox-free system. This allows us to use optimized custom stator winding configuration that are mathematically proven to deliver direct drive capability under varying road conditions. To validate our findings against global benchmark, we conducted a comparative study using the NREL, which is National Renewable Energy Laboratory, situated in USA, vehicle modeling standards. You see the baseline simulation for a standard electrical vehicle configuration. We analyzed the efficiency maps and continuous torque capability of standard 75 kilowatt motor. Note the complexity of the traditional powertrain control and the reliance on transmission logic. We modeled parallel and series transmissions system to see how they compare to our proposed direct drive system. By plotting the fuel converter operation and torque speed maps, we identified the efficiency holes inherent in traditional transmission. Now we move into the technical core of our validation process. Over the next few slides, we conducted a massive array of finite element analysis and transient simulations using the ANSYS electronic suite to ensure this machine would perform flawlessly in the real world. Our analysis began with the high precision stator stacking and stator sketching, followed by a rigorous mesh analysis. By refining the mesh in the air gap and stator teeth, we accurately captured the non-linear magnetic behaviors and saturation levels. Beyond the geometry, we performed a full electrical check. We analyzed the voltage, phase currents, and back EMF for all three phases. The results were excellent. Our sinusoidal back EMF and low iron losses profile ensured that the motor runs smoothly with minimum heat buildup. Crucially, we conducted a sensitivity analysis we conducted a sensitivity analysis on the complete model and verified our plot slot combination. This confirms that our design is not just a prototype for the lab, it is a robust, vibration resistant, and highly effective motor ready for the road. Every plot proved that our gearbox-free architecture can meet the torque demands of a modern electrical vehicle. Moving to the word last. Now we move into the technical core of our validation process. This is the CAD model of our motor and multi-stator of our electrical vehicle motor, which is designed in Pakistan Navy Engineering College, a constituent college of National University of Sciences and Technology. Prototyping stages and machine assemblies we developed. This was not just a single attempt. It was a series of rigorous trials to optimize the winding destiny, housing alignment, and thermal dissipation paths. You can see the progress from the initial core stacking to the fully mounted stator and final assembly. Each iteration allowed us to refine our fabrication, such as improving the insulation of the copper and ensuring the robustness of the magnetic loading frame. This phase is the ultimate proof of our capability to produce indigenous high-performance electrical machines that are ready for real-world EV application. To summarize, we successfully moved from a mathematical concept to a physical high-energy density prototype. Our research proves that by optimizing motor topology, we can eliminate the mechanical gearbox, reducing cost, weight, and power loss. This project served as a vital step forward, localized indigenous EV manufacturing in Pakistan, providing a sustainable alternative to expensive import technology. I would like to thank the Power System Research Lab for the resources and support that made this R&D journey possible. Thank you to the IEEE Symposium for this platform, and thank you all for your attention.
Thank you, Engineer Ammar Akbar. Now,
so basically, we are working on drive-free power vehicle. हम basically outrunner motor को इस्तेमाल करेंगे. जो हमने topology इस्तेमाल की है वो BLDC topology use कर रहे हैं, which is outer runner. And this is a new technology we are working, and we done prototype in our lab, and still we are in the testing phase as well. So yes, yes.
Are you pursuing any industrial collaborations?
Not now, but we are looking forward to collaborate, because we completed the simulations, we completed the hardware in our lab, and it is ready to display.
Any further questions? Thank you, Engineer Ammar sir. Thank you.